Welcome to the Explainer. Today, we're going to pull back the curtain on C++ and dive deep into one of its most critical and, honestly, most misunderstood concepts, memory. You know the feeling, right? Some code you write is blazing fast, and other times it just faceplants. Well, the answer usually isn't in the code you can see. It's in the hidden world of memory. And it all comes down to two key areas that make or break your program, the stack and the heap. So here's our game plan. We're going to meet our two main characters, the stack and the heap, put them head to head, look at the absolute chaos that happens when things go wrong, and then we'll see how modern C++ gives us the tools to master them both. All right, first things first, we need a mental map of what we're dealing with. Let's look at the basic layout of memory that the operating system hands over to every single C++ program. Just picture your program's memory as this big, empty space. From the very top, the stack starts growing down, and from the bottom, the heap grows up towards it. Almost everything interesting in your application happens right here, in these two zones. The catch? They play by completely different rules. Let's meet the stack first. And honestly, the best way to think about the stack is to imagine it's a super efficient, perfectly organized butler for your program. We call the stack automatic memory for a reason. Its entire life is tied perfectly to your function calls. You don't ask for memory, you don't clean it up. The butler just handles it all behind the scenes. It's incredibly predictable, which makes it incredibly safe. The process is what we call last in, first out, or LIFO. Think of it like stacking plates. You call a function, a neat little package of memory called a stack frame gets placed on top. The function does its work, and when it's done, that entire package is instantly whisked away. The process is just brutally efficient. We're talking about a single CPU instruction to allocate or deallocate. But here's the stack's real secret weapon, the thing that makes it so fast. It's all about how it works with the CPU. Because all the data for a function is packed together nice and tight, it's almost always sitting in the CPU's super fast L1 cache. That means no slow, painful trips out to main RAM. And what does that efficiency look like? Well, a stack allocation takes about 0.15 nanoseconds. Let that sink in. It's so fast, it is, for all practical purposes, completely free. Okay, so that's our organized butler. Now let's meet the other character in this story, the heap. And if the stack is a butler, the heap is like a gigantic, flexible warehouse, but it's run by a very, very demanding landlord. See, unlike the stack's simple setup, asking the landlord for space with the new keyword kicks off this whole complicated song and dance. The system has to search for a free spot, maybe it has to split a bigger spot to make it fit, it does a bunch of bookkeeping, and only then does it give you the memory. All of that adds up to some serious overhead. And over time, as you keep asking for and returning chunks of memory, the heap starts to look like Swiss cheese. It gets riddled with all these little holes. We call this fragmentation. And it's a huge problem, because you could have tons of free memory in total, but if it's all chopped up into tiny, useless pieces, you might not be able to allocate the one big object you actually need. Okay, time for the main event. Let's put our organized butler and our demanding landlord side by side so you can really see the difference. So here's the fundamental trade-off, the thing you have to burn into your brain. The stack gives you crazy speed and the safety of automatic cleanup, but it's small. The heap gives you all the space you could want and total control over lifetime, but it comes at the cost of performance and requires you to manage everything yourself. And this table just lays it all out, doesn't it? I mean, look down the columns. It's a total knockout. The stack wins on every single performance metric: cost, speed, fragmentation. The only things the heap has going for it are its huge size and that flexible lifetime. And if you're a visual person, this chart says it all. In a best-case scenario, a heap allocation is over 300 times slower than a stack one. But in the worst case, we're talking thousands of times slower. This is the kind of difference that can absolutely kill your performance. Now, that manual control you get with the heap, it's a double-edged sword. It comes with some really serious risks. Let's take a look at what happens when you tick off the landlord. First up, the classic memory leak. You ask for memory with new, but you just forget to give it back with delete. That little chunk of memory is now an orphan, taking up space forever. In a program that runs for a long time like a server, this is a silent killer that will eventually eat up all your RAM. But this one is even scarier. a dangling pointer. This is where you free the memory, but you keep a pointer to it and try to use it later. This is what we call undefined behavior. You could be scribbling over the memory allocator's private notes, or worse, silently corrupting some other piece of data that now lives there. These are the bugs that are an absolute nightmare to track down. So with all this danger, you might be thinking, is the heap just a trap? And the answer is no. Because modern C++ gives us an incredibly elegant way to get all the flexibility without any of the risk. The solution is this idiom called RAII. Now, it's a fancy name, but the idea is brilliantly simple. You wrap your messy heap resource inside a clean, predictable stack object. When that stack object gets created, it acquires the resource. And when it goes out of scope, and this is the magic part, even if there's an error, its destructor is guaranteed to run, which automatically frees the resource for you. And this is what that magic looks like. Instead of a raw pointer and a manual delete you have to remember, you use something called a smart pointer, like std unique pointer. It looks and feels like a pointer, but it handles the delete for you, automatically. The code is cleaner, it's safer, and it's leak-proof right out of the box. And modern C++ doesn't just give you one tool, it gives you a whole toolkit to perfectly describe how your memory should work. You've got unique PTR for when one thing owns the memory. This should be your default choice. You've got shared PTR for when ownership is, well, shared, and weak PTR for breaking tricky ownership cycles. With these, the most common memory errors just disappear. So the takeaway here is actually pretty simple. You should always prefer the stack. It's safe, it's automatic, and it's ridiculously fast. But when you absolutely have to use the heap for its size or flexibility, don't go it alone. Let modern C++ and its smart pointers do all the heavy lifting for you. And that really brings us back to this question. If we have the tools to do this right, what's stopping us? The path to building safer, more robust software is right there in front of us.